hear me? Mr. Wachira, can you hear me very well?
Yes, Bonamang Boga, I can hear you.
So, okay, thank you. Let me go ahead. So sorry for the 10 minutes. I was trying to unmute myself, but there was a challenge, but I think we have sorted the issue. So welcome to this physics lesson. And I'm going to be presenting. I want us to go through uniform circular motion. So allow me to share the screen. And my assumption is that you are able to see, you see some slides on your screen. We are going to discuss uniform circular motion as our first chapter in Form 4. I know most of us had covered the same with our teachers in class, but I felt that we should revisit the area because maybe we were busy also preparing for the end of term exams, and we were not able to really retain the content. So allow me to start with the terms. The terms used in uniform circular motion. Basically, uniform circular motion, as you can see, involves things like merry-go-round. These ones are found in amusement parks. We have roundabouts. We have some applications like centrifuges that are used in milk industries. What you can see on the screen here, right bottom, is called a centrifuge. That's an application. We also have cases where like the moon revolves around the earth. That's another application of uniform circular motion. So the first term that we talk about is called angular displacement. Angular displacement. And what does it mean? Just from the word angle, then the word displacement. It means we are creating an angle somewhere. So for example, when this body moves from point A on this circle to point B, it's forming a track. It's a sector. In maths, we call it a sector. And this sector is describing a certain angle at the center O, which is angle theta. So this angle theta described by that body from A to B is called angular displacement theta. So in uniform circular motion, when you see theta, it means it's an angular displacement. Definition: this is the angle described by the particle about the axis of rotation in a given time. You don't have to mention the exact words, but you should bring out the definition. For example, you can say, this is the angle subtended at the center of a circular path by a body moving in a circular motion. So from A to B is a certain distance called linear displacement. This is just displacement denoted by S. Just like in linear motion, S stands for displacement. Then R is the radius of the circle. So this angular displacement, theta, is given by S over R. the arc length divided by the radius of the circle gives us angular displacement. So the formula for angular displacement is theta equals to S over R, just like the way it has been written here. Theta equals to S over R. Now this theta is measured in radians. SI unit of angular displacement is radians, not degrees. We know in most cases, when we talk about angles, we mention degrees from 0 to 360 degrees. But now, angular displacement has an SI unit. Now, suppose this body moves from A, goes round the circle, and comes back to point A, then it will have covered 360 degrees. So displacement in that case will be circumference of the circle. So we are going to have theta equals to circumference over radius. And how do we calculate circumference in maths? It's theta equals to 2 pi r over r. So the r's will cancel, and we are left with theta equals to 2 pi. That's why in maths we normally say that 360 degrees is equivalent to 2 pi. It's because when our body describes the motion from A to back to A, it will have covered displacement as 2 pi r divided by radius, which is r, we get 2 pi. So 2 pi equals to 360 degrees. And pi equals to 180 degrees. A half pi, 90 degrees. And so on and so forth. So that's how we also express angles in maths in terms of pi. So this is the formula, theta equals to S over R. You should also be able to define what a radian is. When R equals to S, suppose this distance here from A to B is equivalent to this radius of the circle, then the angle subtended at the center of the circle is 1 radian. So what is a radian? It is an angle of a sector of an arc length equal to the radius of the circle. Angle of a sector of an arc length equal to the radius of the circle. So when S equals to R, then we say that is a radian. The next term is angular velocity. Angular velocity. Just from linear motion, we also talked about velocity, and we said that it's the rate of change of displacement. So when it comes to angular velocity, it means rate of change of angular displacement. Let me see, we have someone who has a question. Yes.
Molly, could you kindly repeat
Yes.
the previous slide?
Definition of a radian.
Yeah.
Okay. He's asking I repeat the definition of a radian. We also have someone else here. Yes. He has disappeared. Okay. Let me repeat definition of radian. So definition of a radian is, I've said that when a body moves on a circular path, let's say it covers an arc length of 2 meters. Suppose the body covers an arc length of 2 meters. And the radius of this circle is also 2 meters. Then the angle subtended at the center of the circle is 1 radian. Because S over R gives us 2 meters divided by 2 meters, which gives us 1. What does that mean? It has traced a path, a circular path equal to the radius of this circle. And therefore, this one, I hope you can see on the screen, from A to B is the same as O to A. 2 meters, 2 meters. So 2 meters over 2 meters gives us 1 radian. This angle will be 1 radian. So definition here, a radian is defined as angle of a sector of an arc. When the angle of a sector of an arc length is equal to the radius of the circle. Or I think this is where the problem is. A radian is simply the angle subtended at the center of the circle. Let me put it in other words. Angle subtended at the center of a circle traced by a body that moves an arc length equal to the radius of the circle. Angle subtended at the center of a circle traced by a body that moves an arc length equal to the radius of the circle. As long as you're able to say that a radian is the angle described when the arc length covered is equal to the radius of the circle, in your own words, then that's the definition of a radian. So I hope I've answered that question. So you are here. Angular velocity, rate of angular displacement. So that means when we take angular displacement theta divided by time, theta over time gives us angular velocity. Angular velocity is denoted by omega, which is on your screen. Looks like a W, but you don't write the normal W. Is a W with some, there's a way in which you write that W. So this is called omega. So when you see omega in physics, it means angular velocity. SI unit is radian per second. Radian per second, written as rad s raised to power -1, or rad stroke s. Rad stroke s. Now, before we continue, you need to know that angular velocity can be written in so many ways. We have about 5 ways we can express angular velocity. The main formula for angular velocity, you can note as Roman 1, is omega equals to theta over time. Roman 2, let's look at another way of writing omega. we have just learned that when this particle describes a whole circle, let's say it starts from here, goes and comes back to the same point, then theta will be 2 pi. So if theta will be 2 pi, then we can say omega equals to 2 pi over time. But because this is a whole oscillation, the circle will be a whole complete oscillation, then in waves, we say time taken for one complete oscillation is called periodic time. So even our small t changes to capital T. So omega equals to 2 pi over capital T, periodic time. That's the second way of expressing angular displacement. The third way of expressing the same, number 3, is from waves, we learned that periodic time T equals to 1 over F. So substituting here, omega equals to 2 pi over 1 over F gives us omega equals to 2 pi F. So the third way of expressing angular velocity equals to 2 pi F. The fourth way of expressing the same, Roman number 4, is we know very well that we said angular displacement theta equals to S over R. Theta equals to S over R. But we have also said that the same, but we have said that omega equals to theta over T, rate of change of angular displacement. Omega equals to theta over T. Therefore, we can say that theta over T equals to S over RT. What has been written here? Theta over T, which is omega, equals to the same omega S over R divided by time. So when we simplify this, because we know that displacement over time is velocity, we can also say now that omega equals to V over R. Therefore, V, which is linear velocity, equals to angular velocity times R. But since we are interested in omega, then this is the fourth way of expressing angular velocity. Omega equals to V over R. Okay, we continue. This one I've already talked about it, angular velocity, periodic time, and frequency. And I've already explained that when the particle or a body makes a complete oscillation, then omega can be equal to 2 pi over T, or omega equals to 2 pi F. This is what has been written here. This is one of them. Omega equals to 2 pi F, and omega equals to 2 pi over T. This one, the first one. So here we have an example. A turntable rotates at a rate of 45 revolutions per minute. What is its angular velocity? So among the four formulas that we have just done, you choose. It is important that you know all of them, then you know when to apply which one. So we are told it's revolving at 45 revolutions per minute. What is its angular velocity? So definitely 45 revolutions per minute can give us frequency, or it can also give us periodic time. So we can get angular velocity by having either omega equals to 2 pi f or omega equals to 2 pi over t, one of them. So let's convert 45 revolutions per second, which gives us frequency f, because frequency is the number of complete revolutions in 1 second. So if 45 revolutions are in 60 seconds, then how many revolutions will be in 1 second? So that will be 1 over 60 times 45, which gives us 0.75 hertz. So the frequency of this turntable is 0.75 hertz. Then we now say omega equals to 2 pi f. So 2 times pi times f, which is 0.75, gives us 4.71 something. You write to 4 significant figures. In your calculator, I think you should get 2 times pi times 0.75. 4.712 radians per second. So that is one example. Example number 2. Okay, we have someone with a question. Let's listen to him. Admission number 360. You can unmute yourself. Yes.
Could you repeat the previous explanation? I've not understood.
The question.
Yeah, I've not understood the question.
Okay. Okay, let me repeat the previous question. So the question is here. This is a turntable. A turntable. I think we know turntables. Those some of them are used by DJs to mix the music and all that. It rotates at a rate of 45 revolutions per minute. 45 revolutions per minute can give us either periodic time or frequency. What is its angular velocity? What is the omega? Now we have learned about 4 ways of finding omega. The first one was omega equals to theta over time. We don't have either of those. 2, omega equals to 2 pi over t. We can get t. 3, omega equals to 2 pi f. We can get f from this information. 4, omega equals to v of r. We don't have v, neither do we have r. So the only option is we are limited to either omega equals to 2 pi over t or omega equals to 2 pi f. So the first thing you do is you find the frequency or periodic time. From the definition of frequency is the number of revolutions in 1 second. But we are given number of revolutions in 60 seconds. And that's why I said 45 revolutions are being done in 60 seconds. So how many revolutions of the same turntable are in 1 second? And when you cross multiply, you get 0.75 revolutions per second. 0.75 revolutions per second. That's the same as 0.75 hertz. which is the frequency. Then we said that omega equals to 2 pi f. So we will now substitute omega, which is our angular velocity being asked, to multiply by 22/7. Pi is the normal 22/7 times 0.75. And when you multiply on your calculator, you will find 4.712 radians per second. Somebody else can decide to find periodic time. So he will start by saying 45 revolutions are in 60 seconds. So one revolution will take how much? How many seconds? So for this person, he will say 1/45 multiplied by 60 will give us what? 1.333 recurring. So this is periodic time. 1.333 seconds is periodic time. Then he says omega equals to 2 pi over t, capital T. So we are going to have 2 times pi, which is 3.142, divided by 1.333. The answer is the same, 4.712 radians per second. So I hope you have understood. We are now on the second example. A model car moves around a circular track of radius 0.4 meters at 2 revolutions per second. The moment you see revolutions per second, that is frequency. What is its one? I think this should be Roman 1, angular velocity omega. So also among the 4 formulas we've learned, you choose according to the quantities given. Here we have radius, and we also have revolutions per second. So I think revolutions per second can give us omega in terms of 2 pi f. So omega equals to 2 pi f. So that will be 2 times pi times frequency is 2 hertz. So 2 times pi times 2 gives us 12.57. 12.57 radians per second. That's our angular velocity, which has been done here. Then Roman 2, I think this is supposed to be Roman 2, the speed v. You also check which formula can give me the speed. The formula is omega equals to v over r. Omega equals to v over r. And I'm interested in v. Therefore, my omega is 12.57 equals to v that I don't have, divided by radius 0.4. So v is 0.4 times 12.57. So 0.4 times 12.57 gives us what? 5.028 meters per second. So that is the speed v. Hope it's clear for everyone. If you have a question, raise your hand. B, find the angular velocity and the frequency of the motion of the car if it moves with a uniform speed of 2 meters per second in a circle of radius 0.2 meters. This is just, they have just changed the quantities, but working is the same. Angular velocity equals to v over r. So you will say omega equals to V over R. That will be our V is 2 meters and radius is 0.2. So the answer is 10 radians per second. That's our new angular velocity. Then frequency of motion, you say omega equals to 2 pi f. The question wants us to find frequency. Therefore, frequency f is omega over 2 pi. So 10 divide by 2 pi, 10 divided by 2 pi. Gives us the answers 1.5912. 1.5912. Okay, let's listen to Alan. Alan. I think he has disappeared. Alan, in case you have a question, you can inquire again. Otherwise, let's proceed. So we have answered part B, where the new angular velocity is 10 meters, 10 radians per second. And then we have the frequency as 1.591, which is here. That takes us to the next term. We are still on terms, which is centripetal acceleration. Centripetal acceleration. Before we discuss this acceleration, you need to know that a body that is in circular motion literally does not accelerate. It moves with uniform linear velocity. V is always constant. As the moon goes around the sun, the earth, it moves with a uniform velocity. But it's undergoing what we call centripetal acceleration because it's constantly changing directions. So you will find questions like, explain why a body in circular motion is said to be accelerating even when the linear velocity is constant. Then the answer should be the body is constantly changing direction. And we know velocity is a vector quantity. So that constant change in direction means velocity keeps on changing. So it's constantly changing direction, hence change in velocity. So that's all about centripetal acceleration. But in terms of calculation, centripetal acceleration A is given by V squared over R. Acceleration is given by V squared over R. Since V equals to omega R, you can also express acceleration as R omega squared. So we have two ways of finding centripetal acceleration. One is V squared over R. The second one is R omega squared. So both of them apply. Let's look at this question. A point on the rim of a wheel has a velocity of 5.6 meters per second. If the rim has a radius of 0.4, I think it's meters, calculate A, angular velocity of the point. So here we have V and R. So angular velocity omega will be V over R, which is 5.6 over 0.4. 5.6 over 0.4 gives us 14 radians per second. B, centripetal acceleration, A equals to V squared over R, which will be 5.6 squared divided by R 0.4. Then you get centripetal acceleration as 78.4 meters per second squared. 78.4 meters per second squared. Someone else can decide to use the second formula, which is acceleration equals to R omega squared. When you substitute, R is 0.4. Our omega is, we got our omegas as what? 14 squared. So the answer will be the same, 78.4 meters per second squared. So that is another term, centripetal acceleration. But remember, a body in circular motion moves with uniform velocity. We say it's accelerating because of constant change in direction. Now, our next part is called centripetal force. So before we look at question number 4, example 4, let's talk about centripetal force. It's denoted by F subscript C. F subscript C. So centripetal force is a force experienced by a body towards the center of a circle. This is a force experienced by a body towards the center of a circle that retains the body on a circular path. It retains the body on a circular path. So without centripetal force and a body is moving in a circular path, then it skids off the circular path. So in most cases, it is argued that this force does not exist. Why? It's because it's a force that is provided for by other forces. For example, a vehicle that is negotiating a bend, it remains on that bend if the friction between the vehicle and the road is sufficient enough. Therefore, centripetal force is provided for by force of friction. If you tie a string, maybe on a piece of stone, take a stone and tie it using as a piece of string, then you whirl. Whirling means rotating it. Then, if there is no tension force in that string, then the stone goes away. Therefore, in that case, centripetal force is provided for by tension force. That's why I'm saying it is argued that centripetal force is provided for by other forces. Therefore, it does not exist. But basically, centripetal force is a force experienced by a body towards the center of the circle in a circular motion. Now, how do we calculate it? From Newton's second law, we know that F equals to ma. F equals to ma. And we've just learned that A is V squared over R. Therefore, F equals to m V squared over R. F equals to mv squared over r. That is how we find the centripetal force of an object in a circular motion. That's one way of expressing centripetal force. The second way is we know that V equals to omega R. V equals to omega R. Therefore, when we replace V squared with omega R, then we are going to have F equals to M omega R squared over R. So when we simplify this, we have F equals to M omega squared R. So the second way of finding centripetal force is F equals to M omega squared R. The first one we've said is F equals to mv squared over R. F equals to mv squared over R and F equals to mv squared R. Sorry, M omega squared R. Now that brings us to question number 4. A body having a mass of 0.5 kgs is tied to a string and whirled in a horizontal circle of radius 2 meters with a speed of 3.16 meters per second. Determine A, the centripetal acceleration. So you're going to do A equals to V squared over R. Acceleration A equals to V squared over R. Substituting, we have our V as 3.16 squared and our radius 2 meters. So from our calculator, 3.16 squared divided by 2 gives us 4.93 meters per second squared. 4.993 meters per second squared. Then part B, the tension in the string. So tension in the string is the one that is providing centripetal force. So you say tension T equals to centripetal force. It's important you explain that T equals to centripetal force. Then you say F equals to mv squared over R, which is now the mass is 0.5 times our V 3.6 squared, and our radius is 2 meters. So from the calculator, we get the answer as 3.24 newtons. 3.24 newtons. If you want, you can also calculate the angular velocity first by saying that angular velocity equals to V over R, which is 3.16 over R, which is 2. That gives me 1.52. 1.52 radians per second. Then you say the tension force equals to centripetal force, which is F equals to M omega squared R. M omega squared R. So substituting, we have 0.5 times 1.52 squared times radius 2. And you get the answer as 3.24 newtons. It's the same. So the working is over here. Have centripetal acceleration, then we have sorry, before we respond to the question, let me just clarify something here that seems not to be okay. Yes, Tim.
Oh, I was just about to ask to clarify B.
Sorry?
The part B, the tension.
Oh yeah, yeah. I was going back there so that we talk about tension. Okay, yeah. Now here, a body has a mass of this and it's whirled in a horizontal circle. What do we mean by horizontal circle? What has been done here is not correct. We have a vertical circle and horizontal circle. Horizontal circle, I don't know how I can put it, but you see, like if a vehicle is moving around a bend, that is horizontal circle. Okay, that's an example of a horizontal circle. When we go back, let me use this diagram here. When you look at, yeah, actually have the two examples here. This one here on the left is called a vertical circle. This one on the right is called a horizontal circle. So here, this boy is whirling this body in a horizontal circle. Therefore, the effect of acceleration due to gravity on this body does not affect, is negligible to the tension force in the string because it's pointing downwards. But the tension is towards the center. Therefore, we don't involve acceleration due to gravity when we are whirling in a horizontal circle like this one. So the issue of minusing or adding mg is not there in any horizontal circular motion like this case. This case on the left is where we involve acceleration due to gravity because it is affecting the tension in those pieces of metal. So what has been calculated here is not correct. This working here is wrong, this part B. The formula is supposed to be tension equals to centripetal force, which is equal to mv squared over r. That's all. The issue of minus ma plus ma does not come in. So when we will be doing vertical motion, I'll be able to explain at what point do we add ma, at what point do we subtract ma. But the moment you see horizontal circle, then centripetal force remains mv squared over r, nothing else. So I hope I'm clear. Okay. So centripetal force I've already explained here. And let me respond to a few questions. We can start with the minor. Yes, minor.
Chair, when you use the mv squared over r, you're still getting the same answer.
It's the same.
Yeah, 2.5.
Okay, no problem. That's fine. Someone else? There's someone who is calling himself U. I don't know how. Yes. Yes.
When you said when you see horizontal circle, the formula is
Horizontal circle is purely mv squared over r. Or you can use m omega squared r. No addition, no subtraction. Yes, Alan?
Could you repeat on how we explain angular velocity?
Angular velocity.
Yes.
Okay. So you can mute yourself. Let me go back to angular velocity. So Alan is requesting that I repeat angular velocity. Angular velocity is just an angle which, is the rate of change of angular displacement. Unless if he was asking about the question, but angular velocity is the rate of change of angular displacement. So angular displacement, which is theta divided by time, because this can also be defined as change in angular displacement per unit time. You can also define it that way. Change in angular displacement per unit time. And I said that we have 4 ways of calculating angular velocity. 1 was theta over time. 2 was omega equals to 2 pi over periodic time t. 3, omega equals to 2 pi f. 4, omega equals to v over r. We have 4 of them. So this was a question that was touching on the same, but it wasn't asking about angular velocity. But if you want to use angular velocity, then start by saying omega equals to v over r. Our v is 3.16 and our r is 2. So 3.16 divided by 2 gives us 1.52 radians per second. Then we say tension equals to centripetal force, which is m omega squared r. So mass is 0.5 times 1.52 squared times 2 meters gives us 3.24 newtons. 3.24 newtons is the correct answer. So in the next lesson, we'll be doing vertical motion. We'll be discussing about vertical motion in a vertical circle, which is this case here. And then after that, we will also discuss about the graphical approach. How do we create a graph? For example, a graph of force against radius. So let me respond to William. The rest, I think we can leave. Have a great day. Yes, William.
Could you explain about angular acceleration?
Angular?
Acceleration.
Angular acceleration is the same as centripetal acceleration. It's the same thing.
Oh, thank you.
Which is the rate of change of angular velocity. Power. Is the same thing. Yes, Abdullahi. Yes, Abdullahi. Can't hear you, Abdullahi. Maybe check your connection. Yes, I can now hear you.
Just kindly requesting if you could send these notes to the group.
Let me send to Madam Kanyiri, then she can forward to the group.
Okay.
Right now, sending her right now. So maybe through your parent, you can access them. Let's hear from 399, Hura.
Sir,
Hura, yes, yes.
can you hear me? Okay, I was asking if when you rotate a bucket or something in a horizontal manner, is the tension uniform?
Yes, tension will be uniform. As long as it's horizontal, tension will be uniform.
Okay.
But in a vertical manner, it's not uniform. So,
Thank you. Yes.
okay. Yeah, thank you for that question. Anyone else? Minor? Okay. Let's stop there. Have a good day. We meet in the next lesson.